ACID in computer science is a set of properties of database transactions intended to provide safety guarantees needed for business data processing. Typical use case being financial transaction processing where the transaction term was landed from. Each letter in a well-known acronym ACID, which stands for Atomicity, Consistency, Isolation and Durability, represents four major guarantees of the transaction paradigm. In this video we'll discuss what each of these letters mean with examples using Oracle Relational Database. Before we go through examples, let's briefly return to accounting business problems that influence many aspects of the development of database systems. In accounting, transactions are records of money movement, typically tracked in journal entries for bookkeeping purposes. A journal entry includes the amount of money moved, where the money went and where it came from. To track from and to, reference objects called accounts are used. Each row in a journal is called a line. Money transfers in financial systems are similar to the law of conservation of energy states. Energy can neither be created or destroyed, only converted from one form of energy to another. This means the system always has the same amount of energy, unless it's added from the outside. In financial system, this preservation is manifested in two sides of business transaction, receiving one, called debit side, and giving one, called credited side. In one transaction, the sum of all credited lines needs to be equal to the sum of all debited lines. Energy, money in this case, only changes state from one account to another. For instance, when you pay your electricity bill, two lines will be marked for transaction. Your checking account will be credited and electricity company account debited, and sum of debit and credit side needs to match. If your bank was charging you compensation, two additional lines could be added to the same transaction. But again, total debit sum would need to match total credit sum for transaction to be balanced. If payment was incorrect, you wouldn't update the original transaction, but rather create a new, also balanced, correction transaction. In that sense, journal entries behave as Git repository. They manage project timeline. Transactions are like Git commits. They should never change and are core building blocks, and give you the ability to travel along the timeline and observe snapshots of project. To find out what is the current account balance, you can accumulate debit minus credit difference of all transactions account was involved with. Although account balance is derived value, it is frequently used, so it's common that financial systems keep cached value to avoid computation. For transaction to be considered valid, it needs to be balanced. All lines need to be journaled, credited and debited side need to have the same amounts, and account balance should be updated to correctly reflect new state. So let's implement overly simplified accounting system in Oracle, but one that is enough to discuss ACID properties of relational database. To demonstrate ACID properties Oracle database provides, we'll create banking schema and couple of database objects to simulate money transfers between accounts. We'll also create accounts for Tim Cook, Satya Nadella and Jeff Bezos and transfer money between them. I've prepared the Docker Compose file to start an instance of an Oracle Express database. This and other accompanying files will be available in Git repository linked in video description. We'll start the services by going to the root of our project and running Docker Compose up-d. The first time it will need to pull the images and it may take some time because they are large ones. I'll be back once our services are started. Once our database is started, we'll open Oracle SQL Developer and create new connection for sys user, which we'll use to create additional users. So we'll use sysdba role, the password is bank, and it's localhost 1521, service name is XC pluggable database 1, so PD1. Test, save, connect. We'll create 4 additional users / schemas by our sys user. One schema called bank will be our application schema that will contain our tables and other database objects, and other 3 users / schemas will be our schemas for Tim, Satya and Jeff, and we'll only grant create session to them. Once we create additional objects in our bank schema, we'll grant execute and other privileges to our other 3 users. Now that we have our users created, let's first connect to the bank user. So the username and password is bank. First, in our bank schema, we'll create a couple of tables and a procedure to enable transferring money between our user accounts. So we'll create table accounts, which has an owner and a balance, which needs to be non-negative. And we'll insert starting balance for our Tim, Satya, and our Jeff user. And if we select from our accounts, we see that Tim has 100, Satya also 100, and Jeff 50. We'll ignore currency in our example. We also need to grant select on accounts to Tim, Satya, and Jeff. This will enable these three users to select from the accounts table to check their current balance. Next, in our bank schema, we'll create tables for transaction and transaction lines. And the transaction lines table will have the transaction master key, account key, the type, is it credit or debit, and the amount being transferred. And we'll also grant select on transaction line to Tim, Satya, and Jeff. We'll also create a procedure to transfer money, which will take our current user account and deduct the desired amount from their account and add it to the to account. It will also insert new transaction with two lines. One line that credits our account, our current user account, and the other line that debits the account we want the money being transferred to. We'll also grant execute a transfer procedure to Tim, Satya, and Jeff so they can call it. I've created connections for our three users. This is connection for our Tim user. In the accounts table he sees 100 balance for Tim, 100 for Satya, and 50 for Jeff, and no data in the transaction lines. This is the connection for our Jeff user, and he sees the same data as Tim user. And this is the connection for our Satya user. He sees the same data in the accounts and the transaction lines table. In Oracle, as soon as you connect to the session, a new transaction is started, so you don't have to explicitly start it. And let's assume that Satya tries to transfer 10 something to Tim and does not commit. Satya sees the account balance in his session that's changed. Tim now has 110 and Satya has 90, and he sees two transaction lines for the 10 amount. Tim, on the other hand, does not see a change. The balances are still 100 and 150, and no transaction lines. This is the I in ACID, isolation. Their sessions are isolated, meaning database ensures that only effects of complete transaction is visible to other sessions if procedure was committed, and no change is seen if transaction is rolled back. And if sessions were modifying data on different tables, they could do so concurrently. Let's commit. We'll go to the Satya session and run commit. And if we now check the accounts from the Satya session, 110.90, transaction lines to transaction lines, but also if we check the accounts in the Tim session, we see the same balance, and we see the same exact transaction lines. Database ensures that 4 operations, 2 balance updates and 2 transaction line inserts were all part of the same transaction. They all happened or neither happened. This is the A in ACID, Atomicity. Transactions could be composed of multiple statements, and database guarantees that they are treated as a single unit, which either completely succeeds or completely fails. We also saw that we can still read accounts and transaction line tables from Tim's session even though Satya's session had transaction running. Serializable isolation means that database guarantees that transactions have the same effect as if they ran serially, i.e. one at a time, without any concurrency, and Oracle uses one of the several weak non-serializable isolation levels, read committed. Read committed makes 2 guarantees. When reading from database, you will only see data that has been committed, so no dirty reads. And secondly, when writing to database, you will only overwrite data that has been committed, so no dirty writes. Tim now has 110 balance. Let's see what happens when he tries to transfer more than he has. Let's say 200 to Jeff. So let's transfer 200 from Tim to Jeff. We get a check constraint validation error preventing the transfer. This is the C in ACID, consistency, which ensures that the transaction can only bring the database from one consistent state to another. Any data written to the database must be valid according to all defined rules, including constraints, foreign keys, and others. This prevents data corruption. More broadly, by providing atomicity and isolation, database also ensures application data consistency. In our case, accounting data consistency, where credit and debit lines must be balanced. This means that certain statements about our data will always stay true. Traveling from one consistent state of our data to another means we preserve our application data invariance. Let's next see what happens when Tim and Jeff try to transfer money to Satya at the same time. And just to remind you, Tim has 110, Satya 90, and Jeff 50. So we'll have Tim trying to transfer 20 to Satya, and then Jeff do the same thing. We see that Jeff's session and his transfer is spinning. We can't complete it. If we have a look at active sessions as our sys user, we'll notice that Jeff has active session in which he tries to update the account balance. We'll also see row level lock on the accounts table, which is a database way to prevent dirty writes, so overwrites to data that hasn't been committed. In our case, Satya account balance that both sessions try to change. If we commit our blocking session, our block session can now complete. Satya now has increased balance from Tim transfer. He has 110 balance. Tim balance is 90 and Jeff is 50. If we have a look at the Jeff session, he sees that Satya has 130 balance and his balance, Jeff balance, is reduced by 20 to 30. But this session is not committed yet. Next, we'll connect to our Docker container and shut down the database. If we now go to our SQL developer and try to execute a query, we'll get a connection error because the database is currently down. And to remind you, this is the committed balance, 90, 110, 50, and this is the uncommitted balance, 90, 130, 30. Let's go back to our container and start up the database again. If we now check the balance in a Jeff session, he sees the balance of the committed transaction, 90, 110, 50. This is the same balance Tim sees and the same balance Satya sees. This is the D property in ACID, durability. Durability guarantees that once the transaction has been committed, it will remain committed even in the case of system failure or database reset in our case, which means completed transactions are recorded in non-volatile memory. This completes our look at the ACID properties of the databases. We saw that transactions are an abstraction layer that allows an application to pretend that certain concurrency problems and certain kinds of hardware and software faults don't exist. A large class of errors is reduced down to a simple transaction abort and the application just needs to try again. Without transactions, various error scenarios, like process crashing or network interruption or unexpected concurrency, mean that data can become inconsistent in various ways.